All right, let's jump in. Now that we've learned about inverse functions, I want to talk about two different types of functions that are defined to be inverses of other functions that we're already familiar with. The first type is logarithmic functions, and we've already actually seen the definition of a logarithmic function. Let me give that to you. All right. The logarithmic function with base a, denoted f of x equals log base a of x, is the inverse function of the exponential function with base a, denoted f of x equals a to the x, so long as a is greater than 0 and not equal to 1. We know that the base can't equal 1 because 1 to the x is just 1, which makes that a constant function, which is not interesting, not exponential. And we also know that the base has to be positive because if the base was negative, there are certain powers we cannot raise a negative number to. The most common example, the most easy example to think of is the 1/2 power, because that is the square root, and we can't take the square root of a negative. Now, we have already looked at logarithmic functions a little bit, but today I want to look specifically at some exponential functions and logarithmic functions and switching back and forth between exponential form and logarithmic form to figure out the inverses of these functions. So let's look at a quick example. Let's find the inverse of f of x equals e to the 2x power. So remember, when we're finding inverses, we replace the function with y, just to simplify things. And then we interchange x and y, so we can write this as x equals e to the 2y. And then we need to solve for y. And in this case, because y is inside an exponent, we need to do something to get it out of the exponent. And there's a couple of options that we have. One of those options is to take the logarithm of both sides. In this case, because the base is e, it makes sense to use the base e logarithm, which is the natural log, which we write ln. So we can write ln of x equals ln of e to the 2y. And then when we have the logarithm of something with an exponent, we have a law of logarithms that allows us to pull the exponent out front. So we can write this as ln of x equals 2y times ln of e. And ln of e is asking e to what power is e? Well, e to the first power is e. So this is just equal to 1. And anything times 1 is itself. So we have ln of x equals 2y. And then to get y alone, we divide both sides by 2. So y equals ln of x over 2. And that is our inverse function. F inverse of x is ln of x over 2. And you can see similarly, if this was something like e to the 8x or e to the 12x, you'd have the same sorts of calculations, and the inverse would be ln of x over 8 or ln of x over 12 or whatever that coefficient was in the exponent. So the trick here is when we've got something in exponential form, we can take the logarithm of both sides and then use that law of logarithms to pull the exponent out, and then we get something in logarithmic form down here. We can also directly move to put this in logarithmic form by remembering that if we have b to the c power equals a, this is the same as saying log base b of a equals c. An exponential equation and a logarithmic equation are just the same relationship written in a different way. And so we could take this exponential equation and we could write this as 2y equals ln of base e of x. If you get comfortable enough with these, you can just go straight into that. All right, I want to do one more, but this time I want to look with a logarithmic function and find the inverse of that, which should give us something exponential. So let's find the inverse of log of 12x minus 15. Remember that when we have a logarithm where there's no base written, log, that refers to the common log, or the base 10 logarithm, similarly to how ln of x refers to the natural log, or the base e logarithm. And I forgot to name this function, so I'm going to call this g of x, cheekily putting it on the right-hand side because there's not room on the left. And so what we're going to do is, to find the inverse, we are going to replace the function name with y. So we're going to write y equals log of 12x minus 15, and then interchange x and y. So we can write x equals log of 12y minus 15. And then at this point, we want to solve for y, but y is inside a logarithm, so we need to convert this to exponential form. And this, I think, is easier for some people than converting the other way. When we've got something as a logarithm, we take the base, which in this case is 10, and we raise it to the power that's on the other side of the equal sign, which is going to be x, and we set it equal to what's inside the logarithm. So in exponential form, this is 10 to the x power equals 12y minus 15. And then getting y alone is just a couple more steps. We can move the 15 to the other side by adding 15 to both sides. And then to get y alone, we want to divide both sides by 12. And the result that we get is going to be this. And that ends up being our inverse function. So we can say g inverse of x equals 10 to the x plus 15 divided by 12. So when we started off with a logarithmic function and we took the inverse, we got a function that included an exponential in it. I really wanted to look at these examples for a couple of reasons. First, to show that when we're trying to find the inverse of an exponential function, we get a logarithmic function, and vice versa. But also because one of the things that students struggle with a lot in calculus classes, not just Calc 1, but also Calc 2 and Calc 3, is a sort of comfortability with a lot of algebraic manipulations. Because oftentimes in calculus, we need to move things around, get them in a certain form, and a lot of students struggle because they don't quite have the practice with algebra that we might hope that they do. And so sometimes when you've got a lesson, whether it's in calculus or in a course before calculus, some of the things in there exist because your instructor wants to kind of get you to flex your algebra muscles and get a little bit more comfortable with manipulating things a little bit. So that is why we are looking at these in this particular way.